Hello, I am Milad Ghaznavi from the University of Waterloo. I present our paper, Fault-Tolerant Service Function Chaining, which is a system to provide fault tolerance for a chain of middle boxes. This is a joint work with my colleagues Elahe Jalalpur, Bernard Wang, Rauf Boutaba, and Ali Majdizadeh. Middle boxes are prevalent in enterprise networks serving different functions. Examples of middle boxes are firewall, intrusion detection systems, and NATs. Packets commonly pass through an ordered sequence of middle boxes called a service function chain or simply a chain. The network operation depends on the reliability of the entire chain. Because of their critical operation, middlebox failures are the largest source of high-severity incidents in one data center study. Although they are only 11% of all network devices, they contribute to 43% of high-severity incidents. Their failures have led to major service outages. As a result, there is significant work to build fault-tolerant middle boxes. Their basic idea is to have a backup instance so that upon failure, the traffic is redirected to this instance. In this example, upon the failure of the primary NAT, the traffic is redirected to the backup NAT. Providing middle box fault tolerance is challenging because the state must be replicated consistently. If the state becomes inconsistent, middle boxes can drop connections, send packets to wrong destinations, or even cause outages. In this example, Alice's connection is dropped due to inconsistent replication. Previous approaches to middle box fault tolerance fall into two categories. Externalized state approaches, which separate the middle box state from its logic and store it into a fault-tolerant data store, and snapshot-based approaches, which take and replicate the snapshots of middle box state. Using existing solutions for chain of middle boxes comes with significant performance overheads. This motivates us to explore another approach to provide fault tolerance for chain of middle boxes. The goals of this approach are providing consistent state replication to tolerate F failures, to minimize the performance overhead during normal operation, and to minimize the disruptions due to failures. To meet these goals, we introduce a new system called fault-tolerant chaining, or FTC. FTC has three main ideas. In-chain replication, where FTC uses the chain itself to provide fault tolerance. Transactional packet processing, which simplifies the development of multi-core fault-tolerant middle boxes. And data dependency vectors, which allows FTC to scale up and down middle boxes across the chain independently. Let's have a closer look on FTC's normal operation using in-chain replication to tolerate a single failure. For each middle box, FTC instantiates a replica. These replicas are co-located in servers hosting middle boxes. The dotted lines shows physical machine boundaries. In addition, FTC adds two other components, a forwarder and a buffer. They communicate to replicate the state of middle boxes at the end of the chain to the servers at the beginning of the chain. FTC components communicate as shown. When a packet arrives, the forwarder piggybacks the state changes of middle box entry with the packet and forwards this packet. As the packet passes through the chain, each replica detaches and replicates the state, track the state changes made by the middle box, and piggybacks these state changes onto the packet before forwarding it to the next middle box of the chain. The buffer releases the packet once the state of middle box entry is replicated at the beginning of the chain. This allows FTC to eliminate the need of any dedicated replica servers to tolerate failures. Upon a middle box failure, FTC selects a server, instantiates a replica. This replica concurrently fetches the lost state, including the state of M1 and M2. Once the state is fetched, FTC instantiates M2. Then FTC reroutes the traffic towards and from this new middle box. To support concurrent packet processing, FTC introduces transactional packet processing. Most existing solutions are single-threaded or batch packet processing. FTMB provides concurrent packet processing, however it uses a complex design to track every read and write on any state variable. FTC introduces packet transactions for a simpler design. It tracks the state changes in granularity of packet transactions. It also does not track read-only transactions. FTC also introduces data dependency vectors to capture the partial order of transactions. Compared to conventional approaches that track the operation of threads, FTC tracks data changes. FTC divides the state to multiple partitions and uses a vector of sequence numbers to track the state partition changes. This allows a middle box and its replica to have a different number of threads, while the state replication remains consistent. This provides more flexibility and improves resource utilization compared to existing solutions that require a fixed one-to-one mapping between middle box threads and those of its replica. Furthermore, data dependency vectors allow a middle box to vertically scale by failing over to a server with different number of cores. For evaluation, we compare FTC with NF and FTMB. NF is a non-fault tolerant system with ideal performance. FTMB uses state logging and snapshots to provide middle box fault tolerance. We implement two FTMB versions with the snapshotting on and off. This slide presents the throughput of chains where we vary the chain length and measure the end-to-end throughput. As shown, FTC throughput is largely independent of the chain length. FTC throughput is twice the throughput of FTMB, and FTC achieves 3.5 times higher throughput compared to FTMB with the snapshots. The throughput of FTMB with the snapshots drops by almost 40% due to periodic snapshots taken at all middle boxes of the chain. Providing fault tolerance for a chain of middle boxes is becoming increasingly important. FTC substantially improves the efficiency of existing solution by treating the entire chain as a fault-tolerant unit instead of making individual middle boxes fault-tolerant. FTC introduces two optimizations to improve the operation of a fault-tolerant chain. Using transactional packet processing, FTC provides concurrent packet processing, and using data dependency vectors, FTC provides concurrent state replication. Please see how these mechanisms work in our paper, and for more benchmark, including FTC improvement on packet latency.
As I put in the chat, please ask your questions on Slack and SIGCOMM 2020-TS11-NFV. So while waiting for questions, maybe I can get us started. So one of the decisions that you make, as you talk about in your video, is this transactional packet processing, right? So now concurrent packet processing, or how to do concurrency safely in middle boxes, is a long-standing issue and independent of fault tolerance. So do you think we should be adopting the transactional packet processing more widely, or why is it restricted to this fault tolerance domain as opposed to being more general?
Thank you very much. That's a great question. I believe that transactional packet processing is a simple and powerful model for concurrency controls in middle boxes. There are two reasons for that. First of all, the number of, usually middle boxes process billions of packets, and they have to be fast, and when they process packets, they only touch few number of state variables. And the time of transaction is also short, and this gives us good opportunities for efficient transactions. So I believe it simplifies. At the same time, it doesn't affect the performance and simplifies concurrency control at the same time.
So while we're still waiting for questions, actually, I'm a bit confused about that answer. So in standard database technology, big transactions are transactions which are more complex, or transactions which which process very little data but do a lot of processing are useful because it allows you to amortize the locking cost. For NNF, of the form that you're looking at, for example, anything that does count, this seems almost the opposite effect, and something like an atomic increment almost seems better. So I don't quite understand this bit.
Oh, of course, sure. Usually middle boxes, they partition the state. They use, so for example, NATs, they assign different pools for when we assign flows to public IP addresses. And usually there is a good opportunity that we can partition the state based on flows and different threads accessing different flows. So it's usually common to basically we can have independent threads that accessing different partitions. As I mentioned, there are two things. First of all, there is good opportunity to partition a state into independent parts. So that threads can operate independently. And second of all, because the transactions are short, if we have two transactions that basically might collide in accessing the same partition, the second one only waits for a short time until the locks are released. So that's why I'm saying that short transactions help here.
Okay, so one last question, and if you can keep it short, that would be very useful. What are the new challenges? So this is from Junji Gong. It's on the Slack channel. What are the new challenges of fault tolerance and middle box chain compared to fault tolerance for network services and distributed systems that we've seen in the past? So, yeah, that's that.
Sorry, would you mind repeating the last part compared to what?
So compared to fault tolerance and normal network services, everything that we've had so far, or in distributed systems where, fault tolerance is basically the bread and butter.
Yeah, the challenge here is that middle boxes process millions of packets per second. So when we want to provide fault tolerance, replicating the state shouldn't become bottleneck because we don't want to lose half of our packets to the replication. So high throughput is and low latency are the keys compared to other services. We need to provide high throughput and at the same time low latency.
Okay, that sounds great.
All right, we have a few questions on the Slack. So the first question is from Wei. Compared to a raw NFV system, what extra resource and overhead does FTC have?
That's a great question. So FTC is like other fault tolerant system introduces some overheads in order to make a chain fault tolerant. These overheads comes with replication. So we need to replicate some state. This comes with some overhead. And in addition to that, it has some locking mechanisms to ensure that while we are basically, because we are supporting concurrent state packet processing, there are some locking mechanisms and there are some overhead in ensuring that we capture a consistent state.
All right. So another question from Wei. Can FTC handle grave failures, such as the middle box can still process packets, but even if it has bit errors or wrong packet format?
I'm not sure what gray failure means, but we assume fail stop model for the failure. So we assume when a middle box fails, basically that stops working. That's our assumption of failures.
Okay, so so let me ask one more question since we have time here.
Sure.
So do you have any restriction on the types of data structure for the network function? Because I'm imagining if the data structure becomes complex, the amount of state you have to carry on the packet can explode.
Yeah, that's a great question. So we don't have, in terms of the type of data structure, we don't have a restriction. We assume general key value store that basically we can map anything to that. In terms of the size, we have limitation. So if it gets really big, so we only are limited to the MTU size. We can, within data centers, we can increase the MTU size, and this will handle most of middle boxes, existing middle boxes. Even with large middle boxes, these by increasing the size of a packet, increasing the MTU size, maximum transmission units, we can handle many middle boxes.